Let's go from current slide. Just wondering, did you go by the the college transfer fair? Yeah, okay. I just wondered how it was. I said it was crazy on the Birmingham campus yesterday, that all the tables crammed into one little place, and it was just a madhouse. I hope they spread them out here. But neither here nor there. And you know about, you won't be here in the fall, right? Okay. Okay. Those are most of the announcements. And you know about the research experience for undergraduate. All right. Any questions on anything we've done so far? Okay, we're in Chapter 2, Matrices, 2.2, Properties of Matrix Operations, and we're just about ready to do example 4. No questions before that? All right, here's matrix, and I get my pen set up, matrix A. A good old 1, 3, 2, negative 1. Okay, here's matrix B. 2, negative 1, 0, 2. Okay. What they are asking us to do is to multiply these two matrices, A, B. Number 1, can you even do that? What size is A? 2 by 2. What size is B? 2 by 2. The 2's are common on the interior, and so your answer is going to be a 2 by 2. What's left over once you wipe out the interior? 1, 2, 1, 2. Okay? The 1, 1 entry will be 2. The 1, 2 entry will be 5. The 2, 1 entry will be 4. And the 2, 2 entry will be negative 4. Okay. Now, in order to do this maybe just a tad easier, I'm going to repeat A. Okay, I hope I do it right. I did. And now we're going to see if we can do BA. Is that doable? Yes. And what size? Same as before. In fact, the only way that we would be commutable if they had exactly inverse sizes, okay? But to get the same size, they would both have to be square, and they are. Okay, let's do BA. One entry would be second. Zero. Excellent. Next. 1, 2. Second. Okay. You're doing 1, 2 or 2, 1? One, 2. Okay, it would be first row of B times the second column of A, right? Wait, okay. Wait, okay. I must be doing something differently. Okay. We're doing the 1, 2 entry, is that right? This one? Okay. So that'd be first row here, second column here, right? Oh. 7, and the 2-1 entry would be 4, and the 2-2 entry would be -2. Okay, what you think about the commutativity of matrix multiplication? Does matrix multiplication commute? Is AB the same as BA? Nowhere close, okay? No, definitely not. Except, we'll run into this later, a few very special cases. When you do get them to be commutative, that means something very special about those matrices. These are not, okay? So in general, let's see if we got the same thing they did. 2, 5, 4, -4, yes, and 0, 7, 4, -2, yes. Now, it says, do not conclude from that example that they are never equal, and they show you two that would be. And let's just do those. Be 1, 2, 1, 1. And -2, 4, 2, -2. Okay. 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 I'm being really lazy. That was 1, 2, 1, 1, and -2, 4, 2, -2. Okay. Let's do AB. The sizes are the same, so they will do. So what's the 1, 1 entry of that product? Two, 1, 2 entry. 0, 2, 1 entry. 0, 2, 2 entry. 2. All right, let's do BA, same way as before. 1, 1 entry. 2, 1, 2 entry. Second. 0, 2, 1 entry. 0, and 2, 2 entry. 2. Whoa, those are the same. Okay? Now, one thing you might note about these, and this doesn't prove anything, but you might note, these two happen to be symmetric matrices, right? And another thing you might note, if you really stretch the imagination, they're multiples of your identity matrix. That's really the more important thing. Okay? We're not going to mess with that now. Later we'll come back and revisit that. Another important quality of matrix algebra that does not have a general cancellation properties for matrix multiplication. That is, if AC is equal to BC, That doesn't mean that A is equal to B. You just can't say, well, let's divide out the C's and you get A equal B. Doesn't work. In fact, example 5 will show that. But we'll see that in the next section that for some special matrices, it will work. But in general, it does not. Doesn't mean it'll never work, but in general. So let's do. Here's matrix A, 1, 3, 0, 1. Here's matrix B, 2, 4, 2, 3. Here's matrix C, 1, negative 2, negative 1, 2. Did I copy them right? I think so. All right, let's first multiply A times C. Can you do that? Yeah, sure, they're all square matrices 2 by 2. And A times C, the middle twos are the same. And your answer is going to be AC is going to be a 2 by 2. Okay? AC now. 1, 1 entry is going to be negative 2. 1, 2 entry will be, really? 1, 2 entry. If I copied it right, I think I did. 1, 2. C now. AC. 1, 2. First row of A times the second column of C. 1 times negative 2 is negative 2. 3 times 2 is 3 times 2. 6. So that would be 4, right? Huh? Oh, I'm sorry. I can't hear well. I thought you said 0. Okay, sorry about that. Okay, 2, 1 entry. Negative 1, 2, 2 entry. 2. All right. Now let's do BC, and let's see if they got it right. Yeah, they did. Good for them. Okay, let's do BC. And that's also a 2 by 2. So that's boop, 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 boop. Okay. 2, 1 entry. 1, 1 entry. Negative 2. 1, 2 entry. Did you say 4? Okay. It keeps sounding like 0 to me. Okay. 2, 1 entry. Are you doing them? Okay, never mind. Go ahead. 2. Sure enough, AB is equal to AC is equal to BC. So therefore, is A equal to B? No, definitely not. But AB is equal to B. AC is equal to BC. But you can't conclude from that that A must be equal to. You can't divide out the C. We haven't even done. In fact, I don't even think there is such a thing as matrix division. So don't even try to do it. There are some circumstances where if AC is equal to BC, then A will be equal to B, but those are rare. They're exceptional. And they're very special matrices that will make that happen. Okay. Now, oh, I thought we had already done this. Maybe not. Have we not done identity matrices?
We talked about it.
I thought we must have, but maybe I jumped the gun. Okay, here is a very special, very, very special kind of matrix, and that's the identity matrix. And in general, it's called I sub n. Now, most of the time when we put a matrix name and do a subscript, we put 2 numbers down there. 2, 3 would be a 2 by 3 matrix. 2, 2 would be a 2 by 2 matrix. 7, 14 would be a 7 by 14 matrix. Okay, let's not do any of those. Okay, but this one only put 1. What does that connote to you? No, it's square. We only put 1 number there, and that indicates a square matrix. So this is a square matrix n by n. Okay, and identity matrices are always square matrices. Okay, and what makes an identity matrix is you have 1, 0, 0, dot, 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 to 0. 0, 1, 0, dot, 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 to 0. 0, 0, 1, dot, 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 to 0. 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 All your diagonal entries are always 1s, including the last one. And everything up to that, dot, 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 to 0, but also this way. 0, 0, 0. Everything in between. There's 1 non-zero entry on each row, and that's on the diagonal. All the rest of them are zeros. That's an n by n matrix. Okay, I put too many things in there. So, what's your I sub 1? 1, that's it. Not much of a matrix. What's your I sub 2? Perfect. I sub 3? Yeah, and so on and so on and so on. Now, it's called the identity matrix. Always square and of order n. This is the order 1, 2, and 3 identity matrix. That one's identity matrix of order n. Okay? Now, we're going to hit on some features of that. So I thought we had already mentioned some, but maybe I'll just mention them that we weren't supposed to yet. Here is theorem 2.4. I'm going to write it down just in case Josh doesn't have the text. I think he does, but in case he doesn't. Theorem 2.4, properties of the identity matrix. If matrix A is a matrix of size m by n, okay, then the following 2 properties are both true. And here's what the first one is. A times I. Now what size must I be to multiply on the right by A? A's and... yeah, okay. But I's are always... second? Square. So that would have to be an I sub n, right? And that gives you what? A. Okay? If you had multiplied I on the left by A, what size would I have to be then? M. A square matrix of size m, because if A has m rows, I on the left has to have m columns. And if it's square, so it'd be m by m. But if it's multiplied by a on the right, it has to have n rows, and because it's a square matrix, it has to be that. So what would I sub m times a be? Also a. Also a. Every time a. As long as I is the proper size, you multiply left or right, it gives you the same value, the same matrix as you multiply. Here is the first example they give. 3 minus 2, 4, 0, negative 1, 1. Now, what size identity matrix would you have to multiply by that? 2 by 2. So that would be, what would it be then? 1, 0, 0, 1. Okay, let's do that multiplication of the matrix multiplication. Is this legal? Now, what size is A, or that first one? 3 by 2. This one's a 2 by 2. So therefore, your answer is going to be a 3 by 2. It better be if it's going to be the same value. Let's see if it is. Actually do the numbers here. The one, okay. 1, 1 entry will be 3. 1, 2 entry. Negative 2. 2, 1 entry. 2, 2 entry. Set. What is it? 0, okay. And 3, 1 entry? Nope. Negative 1. And 3, 2 entry? Yep. No doubt about it. They are the same. Okay? Now, what if I'm going to go to a clean page. Not that it'll take that much room, but it's so crowded without it. The B one, we're going to be multiplying by negative 2, 1, 4. But we're going to multiply on the left by an identity matrix. What size would it have to be? Okay, what size is this one? 3 by 1. So what size would a matrix over here have to be? 3 by 3, and what would it be? 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, let's do the multiplication and see what we get. Oh, what size will this be? 3 by 1 also. It better, well, no, it won't. 3 by 1. Okay, I'll put it as a 3 by 3, which it certainly couldn't be. 3 by 1. Okay, let's do it to it. Negative 2, 1, 4. Hey, that was pretty easy. Don't you want about 15 of those on the test? Okay. So sure enough, that's a 3 by 1, and it's identically what you multiplied the identity matrix by. Okay. Now, this seems like it's just right out of the blue, but it's what they do next. For repeated multiplications of square matrices. Now, these have to be square. We're not doing identity matrices anymore, but doing square matrices. For repeated multiplication of square matrices, use the same exponential notation that we use for real numbers. So therefore, if we have a square matrix, A, that's the square matrix, and multiply it by A, which of course you can do. This is an n by n, that's an n by n, that's an n by n. Multiply it by k matrices, k factors, then you'll get A to the K. Now, where did that come from? I mean, they just yanked it out of the blue or some unknown body part. Okay? Now, so certainly A to the first power is A, and A to the second power would be A times A, and so on and so on. Okay, up to that. I sort of did this backwards. Now, just for funsies, what do you think A to the 0th would be? Which is sort of a bizarre concept. Not 1. I. And whatever size, remember these are all square matrices, it has to be the same size as A. Okay? For A is a square matrix of order n. Now, here are two properties then that you can derive from that. First, if you have A to the jth power times A to the kth power, what would you guess that might be? J plus K. You're absolutely right. Just like we do for real numbers. Okay? And if you had A to the jth power raised to the kth power, that would be J times K. Yeah. Now, how I like to think of this, when you're dealing with exponents, you drop down one level. Now, here's what I mean. The lowest level of operations are additions and subtractions. The next up are multiplications and divisions. The next up are powers and roots. Okay? That's just my way of looking at it. When you're dealing with exponents, when you multiply two exponents, two same bases, different exponents, that's the multiplication middle level, drop down and your exponents are added. When you're raising to a power, that's the third level, the exponents are multiplied. Second. That's my way of thinking. Yeah, that's probably faulty or something, but it just helped me to remember silly little things like that. Okay. Now, they say here, and I think this is absolutely true, for K, J, and K non-negative integers. Now remember in real numbers, we did this too, but then we let J and K be negative numbers, fraction numbers, whatever. Still works. Not here, okay? We don't define, well, we will be defining a -1, but that's not the same as 1 over. Okay, so we're not going to go there. And certainly we're not going to define any root function. Root is, can't even imagine what that would be. So, anyway, let's go to example 7, which is going to do some of that. Here's a matrix A. 2, -1, 3, 0. Okay? They want us to calculate AQ, which you could call it that. So, that would be 2, -1, 3, 0 times 2, -1, 3, 0. Now, I wrote that making it look like -1. It isn't. 2, -1. And then what we'll do is multiply those first, and then we'll multiply again by 2, -1, 3, 0. And from our operations we already have, we could have done it in the other order too, but we'll do it this way. These two are multipliable and will form a square matrix, a 2 by 2 And what will those give us? Say again. 1. Perfect. I think it's -2, isn't it? -2. Next. 6. -3. Okay. And we'll multiply that by 2, -1, 3, 0. And that will give us I don't think so. Oh, wait, I'm sorry, I did it wrong. 2. Okay, I think both of us said it wrong. What did you say? Maybe I misunderstood you. You may have said it right. I'm just not hearing well today. What you get? 1 entry. Huh? -1. Is that what you said? Okay. It's 2 minus 6, isn't it? -4. Okay. Next. -1. Next. 3. Next. -6. Okay. -4, -1, 3, -6. Okay? Now, we just did it. And my question is, so what? Okay? That's the notation for it. That's perfectly fine. There's nothing you can say, oh, I know that is AQ. No, there's nothing special about it. Okay. Now we're going back to section 1.1, mentally anyway. You saw a system of linear equation has exactly one solution, infinitely many solutions, or no solution. You can use matrix algebra to prove this. For a system of linear equations, precisely one of the statements below is true. Now this is just stating what we just did. The system has exactly one solution, it has infinitely many solutions, or it has no solutions. Okay? Now, you haven't proved the thing there. I guess the proof is what follows, and see if you can follow that yourself and see what you get. Now, before we go to transpose of a matrix, let's do the discovery. These usually are a step or two ahead of where we are. So let's clear the ink here. See what we get. Here's matrix A. 1, 2, 3, 4. Real creative matrix. 1, 2, 3, and 4. Here's matrix B. Hopefully a little more creative. 3, 5, 1, -1. All right. Oh. This sort of irks me a little bit. They're asking you to do something they haven't defined yet. Okay? So actually we ought to do the transpose first because they're asking you to transpose. So we'll hold that in abeyance and let's define what the transpose of a matrix is. The transpose of a matrix pretty ugly writing. Not pretty ugly, okay. Of a matrix. Okay. Is formed by writing its rows as its columns. Okay, that's it. So if A is an M by N matrix, and we'll just write it out, A11, A12, A13, dot, 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 A1, N, N columns, okay? A21, A22, A23, dot, 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 to A2N. A31, A32, A33, dot, 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 to A sub 3N. We'll dot, dot, dot down here until we get A sub M, because we have M rows, 1, A sub M2, A sub M3, and then we'll have a dot, 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 and a dot, 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 and a dot, 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 everywhere a dot, dot, and then you get an A sub M N. Okay, there's your matrix A. A transpose, then, is exchanging the rows and columns. Now, these A's have the same values as the A's, corresponding A's over here. A11, A21, A23, no, 31, dot, 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 up to A sub M1. Okay? A sub 1, 2, A sub 2, 2, A sub 3, 2, dot, 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 to A sub M2. A sub 1, 3, A sub 2, 3, A sub 3, 3, dot, 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 up to A sub M3. Dot, 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 down to A sub 1N, dot, 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 down to A sub 2N, dot, 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 down to A sub 3N, and dot, 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 everywhere, dot, dot, A sub M, no. Yeah, A sub M, N. Is that right? Yeah. Same one on both. Okay. Now, this A transpose, though, is a, and this is what's throwing me off here. And yeah, it's an N by M matrix, not M by N, because now it has N rows and M columns. However, in order to keep the subscripts the same for the same values, you see there are N rows here and M columns there. Okay, even those our subscripts are backwards. Okay, so that's what a transpose does. It reverses the subscript, basically. Okay. Now, let me erase what I just did. Now that we know what your transposes are, the definition of it, let's do the discovery here, which uses those two matrices I wrote before I realized they did the discovery, before they discovered what matrices, what transposes were. And I almost wish I'd have erased everything and started writing again. It wouldn't have been quite this long, I don't think. Okay. Now, what discovery, if that A and that B, it says first find AB transpose. So let's first find AB. 2 by 2 by 2 by 2 will be a 2 by 2. So what will it be? Five. Next entry. 3. Next entry. 13. Next entry. 11. All right. We found AB. Now we want to find AB transpose. They put parentheses, I put brackets. It doesn't really matter. Okay, so what would it be?
So that'd be 5, 13,
311. Perfect. Okay. Now, let's do A transpose. One, 3, 2, 4. Is that what you said? Okay. Let's do B transpose. 3, 1, 5, negative 1. Okay. I had a student one time, he always did top to bottom and then went right to left. And it just sounded like he was transposing everything, but I had, okay, now what are you doing? Okay. All right. So we found A transpose and B transpose. So let's multiply those two together. A transpose, B transpose. Second. $18? Is that what you said? Yeah. Perfect. Next. -2. Next. -26. And next. -2 again. Oh, not very interesting. But the next says do B transpose A transpose. Now we got to do that one backwards. Do you mind doing it, or should I write them? Okay, let's do it backwards. Okay, B transpose A transpose. So it'll be row of B times column of A. So that would be 3 plus 2 is 5. Okay. Now, 13. Very good. Say again. 3. Excellent. 11. Look at that. At least in these two, AB transpose is the same as B transpose A transpose. And we'll see that is indeed true. As long as their sizes are right, and of course they've got to be, because these, when you're dealing with these, so it says make a conjecture about the transpose of the product of two square matrices. Now these are square. Select two other square matrices, you check the conjecture. I'll let you do that on your own. Okay. All right. So let's do example 8. How are we doing on time? Oh, we got plenty of time. Huh? Yeah. Okay. Example 8 first says find the transpose of each matrix. First one's a real toughie. Matrix A is 2, 8. What is A transpose? Nope. It's also 2-8, but now it's horizontally 2-8, not vertically 2-8. You exchange the rows and columns. Okay? B. Matrix B is 1, 2, 3. Oh, really creative. 1, 2, 3, 4, 5, 6, 7, 8, 9. B transpose would then be 1, 4, 7, 2, 5, 8, 3, 6, 9. Okay, move. No, yeah, okay, I get it right. C, that's yes in Spanish, will be C, which is 1, 2, 0, 2, 1, 0, 0, 0, 1. What would be C transpose? Say again? The same. 1, 2, 0, 2, 1, 0, and 0, 0, 1. Now, is there anything special about that C that made that true?
Is it the ones going diagonal?
Okay. That, in this case, is true. In reality, it doesn't matter what the diagonal is. Okay? But these are called symmetric matrices because the corresponding things are that. These don't have corresponding things. The corresponding entries across the main diagonal are identical. Okay? It really doesn't matter what the diagonal is, because if it had been a 11745, that would have still been a 11745, because that doesn't change. So what we call this is a diagonal matrix, and the transpose of the diagonal matrix is the same. All right. And D. Zero, 1, 2, 4, 1 minus 1. What is D transpose? Not negative, I don't think. Yeah. 1, 4, negative 1. Right? Oh, lost it. Okay. Yeah, I think we got it all right. All right. Now, the little remark in the left margin says, note that the square matrix in part C, which we noted, is equal to its transpose. Such a matrix is symmetric. So that's the definition of a symmetric matrix, a matrix that's equal to its transpose. Now, therefore, symmetric matrices must all be square. Because if you have a rectangular matrix, it can't be equal to its transpose, because that would be the other dimension. Yeah. So it has to be square. A matrix A is symmetric when A is equal to A transpose. From this definition, it should be clear that the symmetric matrix must be square. Also, if A is the entry Aij, the symmetric matrix, then Aij must always equal Aj for every I not equal to J. And when I is equal to J, then it doesn't have a corresponding entry. I mean, it's equal to itself, basically. Okay, let's go to the properties of transposes. So what we have here are A and B are matrices. Which is what we usually would think, with sizes such that the matrix operations are defined. I'm just going to say appropriately I can't spell sized. Okay. C is a scalar. Okay. Then the following properties are true. 1. Hopefully this will be sort of obvious. If you have A transpose and then you transpose it, guess what you wind up with? A. Yeah, perfect. Okay? The transpose of a transpose is itself. Okay? 2. If you have the sum of two matrices, A plus B, and then you transpose that, what are you going to get? Not completely obvious, but it's A transpose plus B transpose. Now, could you reverse the order of those? Sure, it doesn't matter because addition is commutative. Multiplication is not, but addition is. 3. C, A transpose is the same as C times A transpose. If you think about that for a minute, that sort of makes sense. CA would be multiplying every element in A by C, right? That's what multiplying by scalar does. Then when you transpose that, you could take the C on the outside and then just have A transpose, and then you multiply C times every element in it just like you had before. So yeah, those are the same. Okay? And then the last one is the one we just did in our conjecture or discovery or whatever, that A, B transpose is what? B transpose times A transpose. Perfect. The transpose of a product is the reversed order product of the transposes. All right. Now, number 2 up there, what if you had a whole bunch of them? A plus B plus C plus D plus D, yeah, and then did the transpose of that sum? It would still be A transpose plus B transpose plus C transpose plus D. So you could expand that as many as you wanted to do. Number 4, a little tougher to see, is that this could be expanded. Now I'm just going to do it 3 times. But I'll do it more. A, B, C, D, E transpose is going to be E transpose times D transpose times C transpose times B transpose times A transpose. Okay? That would be, they just did 3, I did till I got tired of writing. Okay? And indeed that's true. Those 2 can be expanded. Now, let's go to example 9. Now, example 9, you can go to larsonlinearalgebra.com for an interactive version of this type of an example. So it wants us to show, we actually have already done it, but we're going to do it again. With this as our A, we didn't do it with a 3 by 3, 2, 1, negative 2. Negative 1, 0, 3. 0, negative 2, 1. B equal to 3, 1, 2, negative 1, 3, 0. Okay. Now, this, I just want you to back up just a tad here. When we did the discovery, it said make a conjecture about the transpose of a product of 2 square matrices. I wondered at the time why they said that, and I guess just because they showed you square. This is going to show They don't need to be square, okay? But we'll see. So first thing we're going to do is AB. What size is A? And B is? So AB is going to be 3 by 2. Okay. First entry. Whoa, that was fast. 6 plus 2. Yeah, that'd be 2. Pretty good. Okay, next. One. Next. What'd you say? Okay. 6. Okay. Next. -1. Next. -1. Next. 2. All right. Next thing we're going to do is transpose that product. So AB transpose is going to be what size? 2 by 3. And what would be the entries? Okay. All right, we've done that. Next, we're going to do B transpose and A transpose. I'm going to do them in that order because that's how we're going to multiply them. So let's first do B transpose, and that's going to be okay, and A transpose. Is that what you said? You're much faster than I was. Okay, now we're going to do B transpose. My superscript didn't come out too well because my screen collapsed on me when I, oh, don't do that. Okay, B transpose times A transpose. What size will that be? Yes, it will. Okay. Okay. Two. Six. No, it should be -1. I must have left off a number. Four. Okay. I'm a bit lost here. Two, no, oh, that is a -2. Okay. I knew I had to have done something squirrely. I did. Okay. So, back up. And that would be 0 minus 4 plus 3 is -1. Right. Good. Next. One. I got a -1. Okay.
Oh, yeah.
Okay, you got it. You do a little bit of this stuff in Math 110. They do a little bit of matrix stuff, not to the extent we're going to be doing it. But the first time ever I used a package like this, it was called Tegrity back then, it wasn't the Screencast-O-Matic. And I was doing this, and I had they had a webinar so we could, perfect it, because the first time I had done it, I said, is there any way you could get me 2 cursors? Because you see, can you see this on the screen when I move the dot? Okay. And I thought if I could only have one in the other hand, then I could do this, because that's how I do these things anyway. And he said, no, we don't have 2. I thought that would be so neat if you could. That's the only thing I could imagine needing that for, but it would have been nice to have, because that's the course, one of the courses I was teaching. Okay, so anyway, we have now shown that those are the same. The discovery before did it for square matrices. This just for these 2 non-square matrices, you do get that. One of them was square, but it didn't have to be. Okay, so A, B transpose is B transpose, A transpose. How are we doing on time? 4 minutes. Let's see if we can get example 10 done in 4 minutes. Okay. Here's a matrix A. 1, 3, 0, -2, -2, -1. Find the product A times A transpose and show it is symmetric. First, we're going to have to figure out what A transpose is. Well, let's do it here. What is A transpose? Oh, what, 3 by 2 you said? Yeah. No, wait, 2 by 3, right. So what will it be? And? Okay. So let's now do A times A transpose. What size will it be? It's going to be a 3 by 3. Ooh, it grew, didn't it? Okay. All right, the 1, 1 entry is going to be a, did you say 10? Yeah. Okay. 1, 2 entry will be a, and 1, 3 entry will be a, five. Okay. 2, 1 entry. Wait a minute. 2, 1. If I did it right, is that 0, 2 times 1, 3? It'll be what? -6. Okay. Next. Got it. Next. 2. Okay. Next. Got it. Next. Next. Five. Okay. Now, what they said is find the product of those 2 and show it as symmetric. Now remember, like I said before, the diagonal doesn't matter. Okay, that's certainly not the same values down there. Last time it was 1, so that was just freaky. Okay, but the opposing are always equal. So that is a symmetric matrix. Now, what they didn't have you do is do it the other way around. Second?
We have 1 minute.
Yeah, I know, but I was trying to see what they do in here. It follows that A transpose is equal to, yeah, because it's symmetric, is equal to A transpose transpose, so it is symmetric. Yeah, okay, I see what they're saying. What they didn't have you do is do A transpose A. Number one, that's going to be a different size, a 2 by 2, but then it should also be symmetric. So we won't do that. Okay, we don't have time. There's an interesting linear algebra supplied down there. So applied down there, not supplied, applied. You can read that on your own. Example 2.2, or exercise 2.2, do any of the odds 1 through 5, they're all at Calc Chat. Do any of the odds 7 through 11, they're all at Calc Chat. Do 13 hits at Calc Chat. Any of the odds 15 to 21, they're all at Calc Chat. 23 should be at Calc Chat, 25 should be at Calc Chat, 27 should be at Calc Chat, and 29 should be at Calc Chat. Any of the odds 31 to 35 should be at Calc Chat, 37 should be, 39 should be, 41 or 43 should be, 45 or 47 should be. They think 47 you might need something special, you might. 49 or 51 should be, 53 should be, 55 should be, 57 should be. 59 should be, and then there's a bunch of proofs and guided proofs. Any of the odds 61 through 69 should be. 71 or 73 should be, 75 or 77 or more proofs, and then 79 should be. And the proofs should even be there. All right, good deal. We'll see you Monday. All right. Have a good weekend.
You too.